these numbers and letters mean?
Well, it's an early version. The instructions have to be punched in by machine code.
Oh, how boring.
Boring?
Back when I was a kid in the 80s with my Commodore VIC-20 and later C64, I had become a whiz at writing code in BASIC, much of which was learned by typing in other BASIC programs from books and magazines. But as I began to acquire more commercial software, when I would attempt to list the program, all I would see is a single line of BASIC with an SYS command and some numbers. I was mystified at how this worked. It was the equivalent of magic to me. Later on, I was told that these programs were written in machine language, or as we later called ML. This wasn't just a Commodore thing. In fact, with most 8-bit systems, 99% of the commercial software and games were written in machine language. This would include your favorite games on the Atari 2600, the Nintendo Entertainment System, Apple II series, and so forth. So machine language was not the exception. In fact, it was the norm. And in this episode, I hope to shed a little bit of light on what machine language actually is. I'm not going to teach you how to code a machine language because that would probably take like 10 hours and be pretty dry and boring. But I do hope to shed a little bit of light on what machine language actually is as compared to other programming languages. And before I tell you what machine language is, I want to start by telling you what it isn't. I'll start by showing you this little demonstration program I wrote in BASIC. I actually used this in a previous episode as a benchmark, and I think it works well here too. This is about as optimized as I can make it running here in BASIC on a 1 MHz machine. Now, back in the day, we had this program for the Commodore 64 called Blitz Basic, and I think it was also known as Astro Speed. Now, at the time, us common folk were under the impression that this would compile your BASIC program into machine language. But that's not actually true. Now, don't get me wrong, the software never claimed to do this, rather it claimed to convert the code into something called P-code. And P-code is just another interpreted language, but it happens to be much more optimized for speed. If you try to list a program after compiling it, it will just say Blitz like this, so the code's no longer editable as BASIC, and I think that's why the common belief was that it was machine language. But anyway, as you can see, if you compare the original program written in BASIC to the one that was blitzed, clearly the blitzed version runs much faster. It's still nowhere nearly as fast as machine language. Now with Blitz, typical results can be anywhere from twice to maybe 8 times as fast, depending on what instructions you're using. So how does this work? Well, for illustration, let's take a look at this simple BASIC program. Let's see how Blitz would optimize it. Well, for starters, any rem statements can be eliminated. I mean, these are only here as comments in the code, but they take up space and slightly slow down execution. And since the program can't be edited anymore, might as well just delete it. The next thing we can do is have a look at where all of the BASIC lines are actually stored in RAM and make note of their actual memory addresses. And then we can look at anything that points to a line number, such as a goto, gosub, or even a next statement, and figure out what it is they're pointing at. Now, normally this is done during execution, which takes time to look up the line number and find its memory address. So to speed things up, you can actually replace the line numbers with actual memory addresses, so no lookups will be done during execution. And of course, we no longer need the line numbers, so they can actually be removed from the code completely. Okay, so here's another thing that could use optimization. Numbers like this stored in BASIC are actually stored as raw text characters, a string if you will. So a number like 53280 is actually stored as 5 separate bytes. You can actually see this if you look at the BASIC program in a machine language monitor. Well, the trouble is these numbers have to be converted from strings to numbers during execution. So again, we can go ahead and convert them now, and that way it saves time when the program is executing. And so these are the types of enhancements that Blitz or similar programs would do to speed up your BASIC programs, but they are still essentially BASIC programs. They're still being interpreted at time of execution, definitely not machine language. But there isn't necessarily anything wrong with this. I mean, if you were good at programming in BASIC, then this certainly gave you an option for some extra speed. So then what is machine language? Well, this is the language that's native to your microprocessor. This is the only language it knows, and every single piece of software you run on your computer, whether it's a vintage computer or a modern computer, has to be in machine language, or your CPU won't know how to execute it. Which means if you're writing code in some other language, it will need to be converted into machine language. Now, there are 2 ways that this can happen. Languages like BASIC, Java, Python, Ruby, and Perl are all interpreted languages, and that means they need a separate piece of software called an interpreter, or sometimes called a runtime environment, which will look at your code one instruction at a time and then convert that into machine language instructions for your CPU. Now, this interpreter must always be present for your code to work. Interpreted code also tends to be the slowest type of code in terms of performance, but also tends to have the easiest learning curve. On the flip side, languages like C++, Pascal, C#, COBOL, and assembly language are run through a compiler, which actually transforms the code into machine language permanently. Now, once this process is finished, you no longer need the compiler for the program to run, although you might need it if you ever want to make changes to the code. Now, these types of programs tend to have much better performance than interpreted languages, but as mentioned before, might have a bit higher learning curve. Now, before you race to the comments section to tell me how wrong I am about Java or C#, please understand that I'm making a generalization here, and I do understand it isn't quite this black and white. The point is, it has to be converted to machine language somewhere along the way. So what does machine language look like? Well, at its core, it's just a bunch of numbers. This small program is an example program which flashes the border on a Commodore 128. The first number here is a CPU command or instruction or opcode, if you will. It commands the CPU to increment a number somewhere in memory. And the next two numbers are the memory address that needs to be incremented. The next number is another instruction, this time telling the CPU to jump or go to some other place in memory to continue execution. And of course, the two numbers following that instruction represent the memory address it's going to jump to. Now, this is actually how early coding was done on computers like the Altair with its panel of switches on the front panel, or computers like the Chem 1. Now, if that seems confusing to you and you're thinking, how on earth would anyone write complex programs in machine language? Well, the reality is nobody did, or at least not since the 1970s. And I gave you this example not to scare you away, but rather to help differentiate between machine language and assembly language. These two terms are often used interchangeably, and while they are closely related, they're not exactly the same thing. It's sort of like the difference between music and musical score. They're very much related, and there is a 1-to-1 ratio between the notes you hear and what is written on the paper, but they aren't exactly the same thing. And since I can't think of a really good way to explain it, I figured the best thing to do is just show you. But first, I want to write a small program in BASIC. Now, this program also flashes the border, and I think this will help illustrate a few things. It's just going to count from 0 to 255 and then write that number to the screen border register. And then we're just going to repeat this indefinitely. Now, this looks like it's going pretty fast. In fact, the border is changing faster than the screen is drawn. That's why the border appears more than one color in places. So that's pretty fast, right? Well, now let's write the same program in assembly language using the built-in monitor. So we're going to start out our program at memory location 1300 hex. And we're going to increase the color value in the screen border. So this D020 here is the exact same number as the 53280 we used in BASIC, just one is represented in decimal and the other in hexadecimal. Also, see these three numbers here? These are the actual machine code that's being stored in the RAM. The stuff to the right is just the human-readable form of that, which we call assembly. Anyway, our next instruction is jump, which is similar to the goto statement in BASIC, and we're going to jump to 1300, which takes us right back here in an infinite loop. So this program is actually simpler and smaller than the BASIC code that we wrote. Okay, so let's exit the monitor back to BASIC, and I'll start the code by typing SYS, which in Commodore BASIC calls a machine language program, and the address is 4864, which is the same as 1300 hex. And so there it is. So this is actually running so fast that the border is changing every few pixels of drawing the screen, making the thing look like this weird pattern. So I'm going to give you one more example program here. Again, we'll start in BASIC, and what we're going to do is count from 0 to 255 again, and we're going to display all 255 characters on the screen. Screen memory starts at address 1024, and that should do it. Let's see how long it takes to execute this code. Okay, about 3 or 4 seconds, so that's not too bad, right? Okay, so now let's do the same code in the monitor. Now, this is just a few lines, so I'll walk you through the code. Now, don't worry if you don't understand all of this. I think you'll get the gist of it. LDX means load X with 0. Now, this just sets the value of the X register to 0. Next, TXA means transfer X to the accumulator. And now STA means to store the accumulator at 400, which is the start of screen RAM in hexadecimal. The comma X at the end just means we're going to add the value of X to the address before the save. INX means to increase x by 1, and then we're going to compare x to 0. Now the reason we do 0 is that if the value is 255 and you increase by 1, it will wrap around to 0 again, since this is an 8-bit system. Now that we've compared, we'll tell the CPU to branch, if not equal, back to 1302. If it is equal, then RTS will tell it to return back to basic. So there we go, pretty simple. Let's execute the code. As you can see, it's so fast that it actually finished before I even lifted my finger off the return key. So I'll show you that again one more time. So now that you've seen assembly language, I'd love to show you this little scene from the Terminator. And what you're seeing here is assembly language, and more specifically 6502 assembly language from an Apple II. Not many people today would recognize this. So why is assembly so much faster than BASIC? Well, as mentioned before, BASIC is interpreted, so for every BASIC command you see here, hundreds of machine language instructions are happening to carry it out. As such, a program in machine language will run at least 100 times faster than anything you can write in BASIC. Now at this point, I think I should stop and mention that there's more than one kind of machine language. Now when you write code in like C or Python, there's a good chance that code is going to run on any computer with any CPU. But machine language is very dependent on the CPU that you're coding for. So code written on a 6502, for example, will not run on a Z80. They're very different languages. But for the purposes of this video, I'm just going to stick with the 6502 because I think it's one of the simplest to understand. The 6502 CPU has 151 opcodes, but it's really not that many in practice. In fact, you only need to remember 56 instructions. For example, if you're using the command LDA, which means to load a number into the accumulator, you can tell it to load a specific number, like 42, or you can tell it to load the number from a specific memory address, like this. Now, as you can see, looking over to the left here, the actual CPU opcodes are different. But as a human, you don't really need to know the difference, as your assembler will take care of figuring out which opcode to use. Now, what I've shown you so far has been using a machine language monitor, which allows you to look at and modify machine code, but you wouldn't really want to write any sort of code in this that was longer than just a few lines, because you'd have to remember a ton of memory addresses for every subroutine. But the worst part is there's no easy way to insert a line of code. I mean, generally, you can only overwrite a line. This is where using a compiler comes in handy. So here's some of my source code for my recent game, Attack of the Petsky Robots. And as you can see, this is written in a text editor and it looks far more friendly with subroutines that have friendly names like search object or display player sprite. And this is where an assembler makes life so much easier. So how does this work? Well, here's a very short little example program written in a notepad. Now, after compiling the program, I'm going to open it up in the machine language monitor and see what it looks like. So the first thing I want to mention is that the actual instructions are preserved one-to-one. There's absolutely no difference here. However, our friendly labels such as screen RAM has been converted into the actual memory address for us. Likewise, the labels I used for the loop have also been converted into actual memory addresses, which of course corresponds to the exact place in the code where it's supposed to point to. And of course, if you just wanted to see the resulting machine code itself, you could look at that as well. And so I hope this better explains the difference between this, which is machine code or machine language, and this, which is assembly language. They're really just two different ways of looking at the same thing. And while back in the early days some coders did have to write software in machine language, the vast majority used an assembler to write code that is much more human readable. So one thing you might be wondering about is why everything in assembly language uses hexadecimal. So I want to explain a few things about it. For those that don't know, it's a numbering system that's based on 16 digits instead of 10, and it just adds A, B, C, D, E, F for the extra 6 digits. Now, the reason this is handy is because when dealing with byte-sized numbers, a single hex digit can represent 4 bits of your byte, which is actually called a nibble, by the way. So 9A is much easier to read than the decimal form of 154. A possibly better example would be looking at memory addresses, which is something you have to do a lot in assembly language. In decimal, the 64K memory range of a CPU would be represented from 0 to 65535, but in hex, it's a much cleaner 0 to FFFF. But where things get really interesting is when looking at a memory address in terms of bytes. So here's the same address in hex and decimal. Now you might recognize this as the border color address of a Commodore 64, which you can use a poke statement to change the border color. Well, in assembly language, this address has to be represented by exactly 2 bytes. And in hexadecimal, those bytes are D0 and 20, which makes total sense. But in decimal, those 2 bytes are 208 and 32, which doesn't appear to make any sense at all. In fact, you have to do some math to actually see that this is right. You'll need to multiply 208 by 256, which gives you 53248, and then add in your 32 from the lower byte, and then you get your final number. So as you can see, programmers find it much easier to just deal with these things like this in hexadecimal. And of course, if they used hexadecimal on Logopolis, that's all the proof you need that this is the best system for computers.
Sorry, E9. 2, 3. Wait. Did you say E9? Look, it says E7 there.
You're right.
One last thing about hexadecimal I wanted to mention is how it's represented. I've been showing it with a $sign in front of it like this, which is the normal way to identify it in 6502 assembly language, or Pascal, or Delphi, or Forth. But another way to represent it is to put a 0x in front of it like this, which is common in 8088 assembly language, C++, C#, Java, Python, and many others. The numbers work exactly the same, it's just a different way of designating it as hex in the compiler. Assembly language in and of itself is not that difficult. In fact, there are certain things that are actually easier to do in assembly language, such as graphics programming, but there are some trade-offs, and there are certain things that are kind of a pain. For example, working with strings. That's a nightmare to work with in assembly language. However, I think the thing that often makes assembly language more difficult is the fact that you have to know how the hardware works that you're coding for. With assembly language, and in the example of the 6502 processor, you have your 56 instructions, and all of these more or less have to do with moving numbers around in memory. So how do you actually do things like modify things on the screen or make music, for example? Well, every chip in the computer presents itself as memory of some sort to the CPU. So in the C64, for example, the video chip presents itself as 47 different memory addresses starting from D1000 to D02E. When it's not memory, we tend to call them registers, but from the perspective of the CPU, it can't tell the difference. So when we write a number to the border color register, for example, the CPU just thinks it's updating a number in memory, but what's really happening is it's updating a register in the video chip. So as a programmer, you have to make yourself familiar with all the registers in every chip on the computer and how they work. And of course, when you move from one computer like the C64 over to another computer such as the Apple II, even though they use the same processor, everything else is completely different. That's why it can be incredibly difficult to port a game from one machine to another. And I think that's why people are often confused when they see that I've written these games like Planet X3 or Attack of the Petsky Robots, and they want me to make a version for their favorite computer. Now, even going between systems that share the same CPU, it's still a pretty big undertaking. In fact, there's a small team of Apple II guys that have been working to convert Petsky Robots over to the Apple II, and as you can see, it's mostly working now. Keep in mind the Apple II has the same CPU as Commodore systems, so a huge amount of the code is reusable between these systems, but it's still a massive undertaking to rewrite all of the audio and video subroutines. But then when people suggest that I make a version of my game for systems that use a different CPU, for example, asking me to make an Amiga or ZX Spectrum version of something like that, at that point it becomes a complete rewrite. So it's no small task. I mean, if it took me a year to write the game in the first place, then it would take me another year to basically write the whole game again from scratch. And I think this is where a lot of people are spoiled by modern programming languages, because if you write something in C or Python, fundamentally you can expect that that same code is probably going to run across multiple different CPUs on multiple different systems with multiple different memory configurations. Machine language basically goes one direction. You can compile a program from a higher level language into machine language, or you can write a machine language program to begin with if you want. But you can't go back the other direction. Much like you can convert notes on a sheet of music into a symphony, it's much more difficult to convert the symphony back into notes. Another example would be scrambling an egg. It's easy to do it in one direction, but unscrambling is a different story. Today, assembly language is more or less a lost art. Modern compilers are pretty good at creating optimized machine code from higher level languages, and computers are also just so darn fast that any speed loss you might have is pretty much negligible these days. I mean, even operating systems like the Linux kernel are written in C. So assembly language today really doesn't offer that much benefit for the modern coder. But if you want to write games for computers that were made in the 1970s or 80s, learning machine language is pretty much a must. And if you do learn it, you'll probably wind up finding out a whole lot more information about how computers actually work. Okay, one last thing I want to mention. If you're looking around at the new studio and you're thinking, well, gee, David, this studio looks pretty boring compared to your old one. Well, it's actually not done yet. So it's just the problem is the old studio has already been dismantled, so I didn't have anywhere to film, so it had to be done in here. But yeah, I'm going to do a whole another follow-up video in another couple of weeks here, hopefully, showing the finishing up of the interior of this studio, and it will look hopefully quite a bit different. So anyway, stay tuned for that, and as always, thanks for watching.